Linear independence. So this is an idea of redundancy. So let's suppose for the moment that V is in the span of V1 through Vm, our usual suspects, our usual list of vectors. Then if it's in the span, that means that it's a linear combination of them. So that means that V looks like A1, V1 plus da 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 up to AM, VM for some choice of constants, or for some choice of scalars. AJ, right? Okay, so then you can ask the question, are these AJs unique? So in other words, is there only one solution to this equation here, one choice of coefficients that'll do it? And this is the question of linear independence. So if V1 through Vm is an independent set, the answer will be yes. So to see this, suppose also that we've got another way to write, or suppose that we've got V written as B1, V1 through Bm, Vm. Okay, and now we subtract this equation from the first equation. Then on the left, we're going to have V minus V. And then on the right, we're going to have the A terms minus the B terms. So if I group the V1 terms together, I can factor the V1 out like this, and so forth. So I have something that looks like this. Okay, so if I can write that, then the answer to my question, so the AJ are unique, meaning that each AJ is equal to BJ. If these two guys are equal, which means this whole term has to be 0, and that has to hold for every single term in the sum. So if AM has to equal BM, then this coefficient here has to be equal to 0 as well. So these guys are unique if and only if all those coefficients are equal, and then those coefficients are all going to be equal if and only if each of these guys is 0, right? So that's the idea. So that leads us to this definition. The list V1 through Vm is linearly independent if and only if the only way for a linear combination of them to add up to 0 is if we take all the coefficients to be equal to 0. So the most succinct way to write that is as follows. A linear combination of these things adding up to 0 can only happen if, or in other words, implies all those coefficients are equal to 0. So this whole implication statement right here, this if-then type statement, that is, so I'm going to call it implication star for the moment, that is the definition of linearly independent. Okay, you can also think of linearly independent as being a negative definition. So I'll give you this as an alternative version. But I just want you to notice that this one here is better for proofs. It might be worse for understanding, but when it comes time to use it in a proof, it's actually the most convenient version. Okay, so so as a negative definition, dependent, we'll define linearly dependent, and then we'll define linearly independent to be the opposite of that, or the negation of that, rather. So we say it's dependent if one of the Vj can be written as a linear combination of the others. And then if that turns out to be false, it is independent. And most of the time I'll just say dependent and independent. I won't bother with the linearly because this is the only kind of dependence we talk about. Okay, so just to see how this negative definition works, suppose, for example, that I've got A1 V1 plus A2 V2 plus da da da. And one of those, and I can do this with one of those AJs not being equal to 0. So suppose we'll just take A1 to be non-zero, for example. Okay. Then I can rewrite this equation as, so I'm going to subtract the this one over, subtract it to the other side, and then divide by A1. And I have this expression. So you can see that if I can write a linear combination here where one of these guys is non-zero, then I can do this trick where I divide by it and subtract over to the other side, and then I have an expression for V1 as a linear combination of the others. So this is supposed to convince you that the idea of being able to solve for one in terms of the others is equivalent to being able to write a linear representation of 0 in a non-trivial way, meaning that one of those coefficients is non-zero.